Okay, next, let's continue the types of statistics. The purpose of collecting and analyzing data is to obtain information. That's what we said before. We want statistical tools to help us understand the ideas of the information. And normally, we are going to break them into two branches. And here are the two branches. First branch, we call that descriptive statistics. It is a type of statistic that involves method of organizing or picturing and summarizing information from samples or population. You can tell from the name, descriptive statistics, which means you want to describe. You want to tell other people what happened. You want to depict the pictures for them. And be careful. You stop at only describe. You do not want to continue your process. The other type of statistic, we call that inferential statistics. It is another method where we are going to involve such as using information to draw information from sample to estimate or infer what happened regarding the population. And generally speaking, they are all type of inferential statistics. Again, you can tell from the name, we try to infer, we try to estimate. So we are not just happy with describe. We want to go one more step. Okay. For example, let's see we have a data on the incomes of 100 employees in a company. This data can be summarized by finding the average income of these 100 employees we select, and we can describe this each and everyone's income to see, okay, you are above the average, you are below the average. That is how we can use the information, right? Okay, you could construct a table, make a pie chart, a bar chart, which will be covered later. They are all examples of descriptive statistics. Inferential statistics, on the other side, remember, we try and make inference. We're trying to estimate. We are not just happy to describe. So if we use the same example, if this group is a representative of the whole company, then you use this 100 employees average, and you say, look, now I have 100 people's information in my hand, and I want to use that to estimate the population information, to estimate the whole company's average. Okay, and if you want to do that, this conclusion will be subject to some error. Why? Because you estimate. And you could even quantify this probability of error. We are trying to do what? Infer, estimating. So this will be what? An example of inferential statistics. Okay. There are two types of random variable. The first one is called discrete random variable. It is a variable that will take finite number of values or countable number of infinite numbers, such as 0, 1, 2, 3, up to infinity. The characteristic of that is there's no intermediate value possible. What means no intermediate value? For instance, you want to count how many eggs a hen can lay in one day, alright? You can see, okay, 1 egg, 2 eggs, 3 eggs, so on and so forth. But no hen can have, let's see, 1.2 eggs, 1.5 eggs, like that, right? Another example. Let the random variable x be the number of telephone calls made from a large city on a given day. And then possible values can be 1 phone call, 2 phone calls, 3 phone calls, like that. Again, you cannot see, okay, I received the 2.1 phone call, right? Okay, other examples of discrete random variables, such as number of children in the family, Friday night attendance, theater, number of patients waiting outside the doctor's office. Alright, that's the first type of random variable. The second type of random variable is called continuous random variable. Continuous random variable can take any values in a given interval. In other words, there's no gaps or interruptions in that interval. Continuous random variable are usually measured data, such as time, weight, distance, etc. Examples can be length, temperature, weight. So, for example, let's have a ruler. Okay, and we can see, okay, after 1 inch, we have 2 inch. But wait a second. Between 1 and 2 inch, how many possible lengths we can have? Well, answer is actually infinity, because you can have 1.1 inch, you can have 1.2 inch, you can have 1.21 inch, you can have 1.25 inch, you can have 1.256 inch. As a matter of fact, as long as your ruler is more and more accurate, you can always have what? More digits, right? After the decimal place. What that means? That means take a random variable, and that random variable is continuous. Okay, another example is thermometer. Again, after Fahrenheit 50, that is Fahrenheit 60, but between them, what's happened? All possible degrees you can measure. You can see, okay, I measured with my thermometer, I get 51 degree. Other people say, look, I have electronic thermometer, and I can take the measurement as accurate as 51.21 degree. Okay, some other examples, such as calories in a hamburger, amount of sugar in an orange, so on and so forth. You can normally, whenever you talk about time, space, such as volume, weight, they are all typical examples of continuous random variable. And based on the fact, such as length, weight, time, volume, you can have some other examples which is associated with them. For example, space. We know it is random variable, such as the ruler, such as distance you walk. Then some other variables, if they are related. For example, if you talk about the distance, you're jogging. You see, you're jogging for 3 miles. Then that jogging distance itself is a random variable. So how about the speed? Like how fast you run? And it is what? Random variable also. Why? Because we all know, if you take physics, you know, speed is what? Distance divided by time, right? So distance divided by time. Since distance itself is random variable, then of course speed will be random variable also. And based on the same idea, accelerating factor will also be random variable. Okay, so some other examples, such as weight of a firefighter, this will be a continuous variable. Since firefighters' weight can take any values between 100 and 250, just for example, okay, illustration purpose. So for example, 151 pound, 153.5 pound, 174.3 pounds, so on and so forth. They are all what? Continuous random variable, because there's no gap. Okay, time, as what we said before, is a continuous random variable. Here's an example of a stopwatch. It is a digital stopwatch with accuracy up to 1 out of 100 seconds for sports competition. And this is a graph for women's 100-meter backstroke in 2012 London Olympic Games. And here's the final result. Let's take the top 3 as an example. You can see the top 3, if we only measure second up to single digit, then all the first 3 are actually tied, because they all have what? 58 seconds, right? So which means you really have to improve the accuracy in order to see who won the gold medal, who got silver, and who got bronze. And remember, we are handling what? Continuous random variable because it is time. Therefore, if we use the digital stopwatch, we can say, okay, the winner is 58 seconds, 0.33 seconds, with the silver medal 58.68, and the bronze 58 second 83. In other words, because time is continuous, so there's always what? Room for improvement in terms of accuracy, because there's no gap.